Hello! I'm Professor Von Schmohawk, and welcome to YU. In the last chapter, we saw that when a system of three linear equations in three variables consists of three planes whose intersection forms a line, the system has infinitely many solutions. And these solutions can be described parametrically using either parametric equations or an ordered triple. To demonstrate how this is done, we will start with a system of three equations which describe three distinct planes that intersect along a line. When solving a system of equations using the elimination method, we typically start by eliminating one of the variables. So let's say we choose to eliminate x. To eliminate the variable, we pick a pair of equations to add, first multiplying one or both equations by a constant if necessary to make the sum of the x terms 0. In this example, we can pick any pair of equations, so let's select the first two equations and multiply the second equation by -1 in order to make the x terms cancel. Adding the equations, we get 10y plus 10z equals 10, or dividing by 10, y plus z equals 1. Now we pick a different pair of equations and eliminate the same variable x. This time, let's pick the first and third equations. Multiplying the third equation by -1 and adding the equations, we get 6y plus 6z equals 6, or dividing by 6, y plus z equals 1. This gives us a system of two equations in two variables which we can try to solve to determine the values of y and z. But since both equations are identical, when we multiply one equation by -1 and add the equations, we get 0 equals 0, indicating that the given system has infinitely many solutions. We have seen that eliminating x using the first and second equations gives us y plus z equals 1, and eliminating x using the first and third equations also gives us y plus z equals 1. Will we always get the same result no matter which pair of equations we choose? Let's see what happens if we use the second and third equations to eliminate x. Multiplying the third equation by -1 and adding the equations, we get -4y minus 4z equals -4. Or dividing by -4, we once again get y plus z equals 1. So no matter which pair of equations we choose, we always get the same equation, y plus z equals 1. And therefore, we will always end up with the result 0 equals 0. The equation 0 equals 0 contains no information other than to indicate that the given system has infinitely many solutions. However, the equation y plus z equals 1 can be useful in creating a parametric representation of the solutions. Since it contains only two variables, it makes it especially easy to create parametric equations for y and z. We create the first parametric equation by equating either y or z to the parameter t. Depending upon whether we choose y or z, we will get slightly different parametric equations. However, even though the resulting parametric equations may be different, they describe the same line. For this example, let's equate the variable z to t. Remember that we need one parametric equation for each variable, x, y, and z, and each equation equates that variable to a function of t. Our first parametric equation, z equals t, equates z to a function of t, albeit a simple function. Since z is equal to t, we can substitute t for z in the other equations. Now we need parametric equations for x and y. Since the equation y plus t equals 1 contains only the variables y and t, we can use it to express y as a function of t. Subtracting t from both sides gives us the equation y equals 1 minus t. Now that we have parametric equations for y and z, we can create a parametric equation for x by substituting 1 minus t for y in any of the three original equations. Since all three equations contain x, we can use any one of the equations to create a parametric equation for x. So let's choose the first equation. Replacing y with 1 minus t, we can now solve for x. We start by distributing 8 to the terms in parentheses. And combine like terms, giving us 3x plus 8 minus 4t equals 18. Subtracting 8 from both sides we get 3x minus 4t equals 10. And adding 4t to both sides, we have 3x equals 10 plus 4t. Or dividing both sides by 3, x equals 10/3 plus 4/3 t. We now have parametric equations expressing x, y, and z as functions of t. The solution set can also be represented parametrically as the ordered triple 10/3 plus 4/3 t, 1 minus t, t. This ordered triple describes the line of intersection of the planes and the solution set of the system of equations. During the process of eliminating x, we found that no matter which pair of equations we use, we always produce the same equation y plus z equals 1. Therefore, when we eliminate another variable, we will always end up with the result 0 equals 0. If instead of eliminating x, we had chosen to eliminate y, each pair would have produced the equation 3x minus 4z equals 10, and we would still end up with the result 0 equals 0. Likewise, if we had chosen to eliminate z, each pair would have produced the equation 3x plus 4y equals 14, with the same end result 0 equals 0. So no matter which variable we eliminate, and no matter which pair of equations we use to eliminate that variable, we will always end up with 0 equals 0, indicating that the system has infinitely many solutions. But it turns out that even though eliminating different variables produces different equations, as long as we start out by setting z equal to t, the parametric equations will be the same. It is important to remember that there are an infinite number of parametric equations which can describe the same solution set. In fact, we would have ended up with different parametric equations if instead of setting z equal to t, we had set x equal to t or y equal to t. These changes would have produced different parametric equations and different ordered triples. However, these different parametric representations are all valid and would still describe the same solution set. There is no single unique set of parametric equations for a given solution set. Many different parametric equations can describe the same solution set. The point described by different equations may lie at a different position on the line for a given value of the parameter. Likewise, as the value of the parameter changes, the point described by different equations may move along the line at different rates. But although the equations may be different, as long as they describe every point on the line, they are a valid description of the solution set. In this lecture, we have seen that a solution set corresponding to a line in three-dimensional space can be mathematically described by parametric equations. And we have seen how these parametric equations can be calculated. We also saw that in systems containing planes which intersect along a line, when we eliminate a variable, the same equation will always be produced, no matter which equations are used to eliminate that variable. In the next lecture, we will see why this happens by looking at the process of variable elimination geometrically.